Hi, thanks for joining me today. I've got a fun integration video for you. We want to compute the integral from 0 to 1 of x to the pi minus 1, all divided by log x dx. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the way we're going to solve this problem is in fact by considering a more general class of integrals. So we're going to consider this function here, I of theta, and it's going to be the integral from 0 to 1 of x to the theta minus 1 all over log x dx. And essentially what we want to do then is find a closed form for I of theta, and then just plug in theta equals pi, and then we'll be done. Okay, so the way we're going to do that is by starting from this thing here, differentiate both sides with respect to theta. So on this side, differentiate with respect to theta, I get I prime theta. On the right hand side, I get d theta of this guy here. But I can use a trick, I can bring this derivative inside the integral. So if I get rid of it from here, and then just plop it here, so d theta of this guy here. So we're differentiating the thing in brackets with respect to theta. Okay, so well, what is that? That's the integral from 0 to 1 still. And now we've got x to the theta over log x minus 1 over log x. So this minus 1 over log x is going to vanish when I take the derivative, because remember it's independent of theta. So I've just got to differentiate x to the theta over log x. Or that 1 over log x we can kind of treat like a constant. And then we're taking the derivative of x to the theta with respect to theta. So remember x to the theta, maybe if I write it explicitly, x to the theta is just e to the theta log x, like so. So when I differentiate this guy here, I'm just going to get a log x times e to the theta log x, which is just log x times x to the theta. So all in all, this is just equal to log x times x to the theta, and then I've got my dx here. And now you can see this log x cancels very nicely with this 1 over log x. So this can all be got rid of, and I'll bring this over here. We've got x to the theta dx. So I prime of theta is nothing but the integral from 0 to 1 of x to the theta dx. Well, this is a very straightforward integral. We can just go ahead and compute this. This is going to be 1 over theta plus 1 times x to the theta plus 1 between 1 and 0. But of course, when I plug in 1 to that, I'm going to get 1. And when I plug in 0, I'm going to get 0. So this is just 1 over theta plus 1, like so. So I prime of theta is 1 over theta plus 1. So the derivative of I with respect to theta is 1 over theta plus 1. Well, that means that I of theta is just going to be log of theta plus 1 plus some constant c. Okay? Because the antiderivative of 1 over theta plus 1 is just log of theta plus 1, because if you differentiate this guy here, you get that guy there. So we've got I of theta is log of theta plus 1 plus c, and remember all we wanted to do is plug in pi, and we get what I of pi is, sorry. But first we have to deal with this c here. We're not really sure what that is, but we can do that very nicely. If you remember how we defined I of theta was just the integral from 0 to 1 of x to the theta minus 1 all over log x dx. We notice when theta is 0, we get x to the 0, which is just 1 for all x. So this numerator is 1 minus 1, which is 0, and hence we're just doing the integral from 0 to 1 of 0. So that means that I of 0 is just 0. So we can kind of use that as a boundary condition if we want to try and work out what I of theta is. So I of 0 is 0. So if you plug in 0 into this, we get I of 0 is log of 0 plus 1, so log of 1 plus c. So I of 0, we know, is 0. So 0 equals log of 1 plus c. Log of 1 is already 0, so in fact we get that c is just equal to 0, which is really nice. So in fact we get that I of theta is just going to be log of theta plus 1. And as I said, all we're interested in is I of pi. So we get the I of pi, which we know is the integral from 0 to 1 of x to the pi minus 1 all over log x dx. This guy here is simply equal to log of pi plus 1, like so. So really neat closed form there. Okay, that solves our problem. I hope you have enjoyed this. This technique is used quite a lot, I guess, when you're trying to solve certain integral problems. When it looks like you've got something that's quite difficult to deal with, sometimes it's, in theory what we did is we made this problem harder by introducing theta, but in fact, because we just used some simple derivative techniques, and then kind of undid those to work out what I of theta was, it actually made the problem a lot easier. Okay, so this technique is used, so I guess if you've not seen it before, you can add it to your arsenal of integration tools. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.